excited to be here. I've heard a lot about Hack Reactor and I've never been here, so it's exciting. Can everyone hear me okay? Yeah? Okay. All right, so thanks to Alex for the intro. I'm Emily. I'm a core developer at Meteor. Has anyone not used Meteor and doesn't know anything about Meteor? Okay, so Meteor is a full stack, all JavaScript framework. It's designed for making web applications that are sort of different than your traditional request response type applications. So some of the things that we do really differently are very thick clients. So that means all the code for rendering the templates, for maintaining an in-memory database cache, for doing full reactivity on the client side. So when your data changes from the server, automatically lots of things on the client change, like your templates re-render to match the new data from the server. So Meteor is a framework for developing these new style applications that are constantly dealing with data, switching from, transferring from different clients to different clients, and constantly, very easily keeping everything updated. So I've been at Meteor for about 4 months now, and I joined Meteor from academia, and I was working there. I was at MIT and Stanford, and I was working on web security research, and I mostly worked on client-side crypto and making client-side crypto secure, fast, useful, all those good things. So I joined Meteor partially because I was really excited about this new world of web apps where there are a lot of new cool web security properties, and some of that's what I'm going to talk about tonight. So what I'm going to cover is, basically I just want to kind of share whatever I can that would be interesting to you. So, you know, feel free to jump in, ask questions, tell me to speed up or slow down or whatever. I'm planning to go over some kind of common web security areas, so some common attacks, some common things that developers tend to get wrong, and I'm going to try to give a feeling for how to prevent them. And the reason that I'm choosing to talk about the things that I'm going to talk about are because I think Meteor has something a little bit different in it in each of these areas that kind of maybe gives us a feel for how the web security landscape is going to change as apps change on the web. So what I'm going to talk about is start with trying to give a feel for why the web is a little bit of a dangerous place, and what about the web makes some attacks that we see very frequently on the web, what makes those attacks possible that aren't possible in different computing environments like phones or desktop computers. Then I'm going to go into these kind of more detail into these specific attacks and security-sensitive code that you might be writing, and try to give a feel for those areas in more detail, both in the kind of traditional web app style and in the Meteor world where you have thick clients and data constantly pouring in from lots of different clients and being synchronized and re-rendered. Okay, so first, before I jump into what really makes the web kind of a dangerous place, I'm going to just give one piece of background information, and maybe a lot of you already know it, but I just want to go over the same origin policy, which is kind of the basic security policy on the web. And what the same origin policy says is that an entity on the web is an origin. So what's an origin? It's this tuple of protocol, host, and port. So for example, HTTP example.com is an origin where the protocol is HTTP, the host is example.com, and the port is implicitly port 80. So web browsers define an origin as kind of a unit of trust or an entity on the web. So different origins are not allowed to communicate with each other very well. They're not allowed to share data very easily. There are mechanisms for them to communicate, but it's generally restricted. And within an origin, so any code all on the same origin is generally considered at the same level of trust. So example1.com cannot, for example, read cookies set by example2.com because they're separate origins, their cookies are not shared. On the other hand, example.com can read any cookies set by other code from example.com. So within an origin, everything's at the same level of trust. Between different origins, everything's very segregated by the web browser. So this is really how security is defined on the web, and I just wanted to make sure we're all on the same page with that because I'm going to be talking about origins a lot. Okay, so I'm going to give you now a long list of reasons why the web is a dangerous place. And a lot of times when people talk about the dangers of the web, one of the first things that comes up is what people sometimes call drive-by code execution. And what this means is that when you are a client and you go to send a request to a web server, you get back an HTTP response, and the browser kind of immediately executes that as code. By the way, let me know if I'm in the way for any slides here. Everyone see okay? Okay. So this drive-by property is that your browser sends a request on your behalf. Immediately the response comes back and it gets executed as code. So parsed and rendered as HTML, and the JavaScript also gets parsed and executed. So this seems so normal to us, but if you think about any other computing environment, this is really not the case. So if you think about an Android phone, for example, you want to run some software on it. So you go download an app, you install it, you even get explicitly asked for the permissions that app has, and only then does the software actually get to run. Or even on just a computer, a desktop computer, you have a native operating system, you want to run an application on top of that operating system, you go download the software. If you're super paranoid, which everybody should be these days, you maybe even verify that the code you downloaded is the code that you meant to download. Maybe you do that by taking a checksum of the code and comparing it against a checksum from a trustworthy known source. And only then do you compile it, even maybe sometimes yourself, install it, and then run it. So in other computing environments, you have this long process where at any step in the process, you can kind of verify that the code's from a trusted source, that the code is the code that you intend to run. But on the web, you really don't have that chance. You go to a website, you download the code, you run it immediately. Another thing that makes the web a little bit, one more thing I wanted to say about this, sorry, is that in the web security model, we generally assume that the attacker can run code in your browser, and this is exactly why. So I'll talk about a lot about attackers kind of, just getting code to run in your browser, maybe tricking you into visiting a link, or tricking you into clicking on a link in an email they send you. And because of this drive-by code execution model, we generally consider it very easy for attackers to get to just run code in your browser. So statelessness is a property of HTTP, which is kind of the protocol that the web runs on. And what I mean by stateless is that when your browser is talking to a web server, it sends a request, gets a response back, maybe sends another request, gets another response back. And these two requests are processed by the server totally independently. So there's nothing in this request that ties it to this previous request. And in fact, they could be handled by two completely different machines. And that by itself is not a bad property. There's nothing inherently bad about statelessness. But one of the mechanisms that was introduced to deal with statelessness, which is HTTP cookies, have had a lot of problems in the past. And I'll talk a little bit about attack vectors involving cookies, and that's maybe one of the reasons why a model like Meteor is a little bit less attack prone. Oops, because Meteor uses a stateful protocol. So what this means is when you open up a Meteor application in your browser sends a request and the response comes back, and it contains all the HTML and JavaScript for the entire application. And after that, you set up this WebSockets connection, which is sort of like a normal TCP connection, and everything on this connection is data. And this connection is long-lived and it's stateful. So there are no cookies in Meteor, and I'll talk a little bit later about why that leads to some different security properties, some of which are better, some of which are possibly worse.
Can I ask you just?
Yeah.
Creating a TCP like long-lived connection is in any way more demanding for the server than it's like if you're receiving a lot of requests?
There are some different properties that you would require of a server architecture. So, for example, so one thing that happens, not all browsers support WebSockets. So we use a library called sock.js, which falls back to HTTP polling if WebSockets isn't available. So that can obviously be expensive, and it also requires something called sticky sessions. So if you have a server architecture where you have multiple different proxies, multiple different servers kind of accepting connections. If you have one client who's doing this HTTP polling, they have to always go to the same server. So their requests can't always be routed to different servers in your pool of servers. So that's kind of like an extra property you need on top of your servers that not all server software requires. As far as like, I'm not sure how you would compare performance of, there's some memory usage required, but on the other hand, you're not constantly kind of opening and closing TCP connections. So I'm not sure what the exact performance comparison is, but there are different requirements, I'd say. So I'll talk a little bit later about how we kind of take advantage of this long-lived connection to do authentication and why it doesn't involve cookies. The final thing I'll say about why the web is kind of a dangerous place is because it's very common on the web to see these responses come back from a server, and they might contain a whole bunch of data from the database rendered inside a template with some JavaScript mixed in. And it's not immediately clear from that what's data, which might be kind of user-provided data, which shouldn't be trusted, what's code provided by the server, and sometimes there can be a mix-up, and this is kind of a classic source of security vulnerabilities all over the stack. So the fact that an HTTP response might contain code or data or a mix of both has historically led to a lot of confusion on the web, and this is another area that Meteor tries to make a little bit less bug prone, and this kind of comes out of this flow that I just showed, where the request and the response contain all the code for the app, and then after that it's just data on the wire. So we hope that by kind of separating out this first response has all the code but no data, and everything on the wire after that is data, we hope that kind of clearly separates things and leads to less confusion. Okay, so now I'm going to go into some more detail about specific areas that tend to be security-sensitive code. And I'm going to start by giving an overview of user authentication and password storage. So I'm going to kind of go over what a traditional auth-flow in a web app looks like, what kinds of things you should look out for, and maybe what kind of code you should be very careful about. And then I'll go into what Meteor auth looks like and how it can kind of be interesting to look at authentication in a slightly different model. So this is what a normal auth flow in a traditional web app looks like at a high level. Your browser has a username and password that they want to log in as with the server. And so they send this username and password to the server. The server verifies that the password is valid. And in response, it sends back a session cookie. And the session cookie gets set in the user's browser, and then it gets sent on every request that browser makes to the server after that. Of course, you can see there's sensitive information being sent on every request here. So it's very important that this login flow and all authenticated requests at the minimum go over SSL. So you want to make sure that your site has an SSL certificate and that ideally your whole site is just only accessible via HTTPS. And I want to point out that it's not just the password that's sensitive. The password is a very high value target, but if an attacker eavesdrops on the session cookie, they can then act as the user and do everything the user can until the session cookie expires. So the session cookie also is a very high value target, and that's sent on every single request. So every single request should ideally be over SSL. So I'm going to go into a little bit more detail. I glossed over some things here in this high-level overview. The first thing, as I said, the server verifies that the password is valid. So you don't want the server to just store the passwords in the database and just check the password that it gets from the client against the password in the database, because databases get leaked all the time, and if an attacker gets their hands on a database with some plain text passwords, that's bad. So instead, what you often see sites doing is they store a hash of the password in the database, and a hash is technically a cryptographic one-way hash function, which is a function where if I put an input into the function, I get an output, and it's very, very, very difficult, practically impossible, for an attacker to figure out what input when they are given just the output. So you might have heard of things like SHA or MP5, which are hash functions. Some of them have weaknesses, some of them don't, but those are all considered reasonably decent general purpose hash functions. The question is, are those the hash functions that you want to use for hashing your passwords? And you can probably tell I'm hinting the answer is no. The trivia question I have for you is if you have a database where every password in it is hashed with a hash function like MD5 or SHA-1, these are hash functions that probably your attacker is not going to do much better than just brute forcing, guessing every possible password, looking at the hash and comparing that at the hash in the database to see if that's the plain text password. So my question is, how many of these guesses do you think that an attacker could do in 1 second?
A few tens of millions, hundreds of millions.
Hundreds of millions?
Low billions, maybe. Depending on their graphics card.
Yeah, I'm talking about state of the art. Like, what's the record?
Billions.
60 billion to be precise. Yeah, so that's a lot of passwords. With the most naive attack you can imagine, which is just kind of guessing random things, not going in any order according to like most common passwords or anything like that. So that's with the most naive guessing strategy, though with a lot of GPUs, it takes less than 1 minute to crack like a pretty good password, 7-character alphanumeric password. So you do not want to use these hash functions to store your passwords. You might hear about password salting. I'm not going to go into a lot of detail about that, but it's actually, if someone tells you to just put a salt and your password together and put it into a hash function, that's also no good. What you want to do is a hash function called bcrypt or scrypt, and these are called password hashing functions. And unlike general purpose hashes like SHA or MD5, they're actually designed to be slow. And it's one of those rare times when you want, like, slow is better. It's very rare that you want your anything to be slow. But in this case, what we're really looking to do is just slow down an attacker. So an attacker is guessing passwords. We just want it to be very, very slow. Every time they guess a password, they have to slow down, hash it. It should take, as long as we can realistically make it take without slowing down our real honest users too much. Another really cool thing, oh yes, go ahead.
Out of curiosity, I was under the impression that those were only slowed for registers of 32-bit and 64-bit sizes. I mean, if you built a process to track those, wouldn't they go really fast?
Well, there's no way to crack them. You mean to like specifically?
I mean, like build an ASIC for bcrypt and scrypt.
So what bcrypt and scrypt are doing under the hood is iterating known hash functions many, many, many thousands of times.
Okay.
So there's no known way to break them better than to just try guesses.
Okay.
As far as I know. Another really cool thing about them, besides that they're slow, is that they're scalable. And what I mean by scalable is that they have a work factor. So one of your inputs to the hash function is a work factor, which is an integer, and that controls how many times these hash functions iterate. So I think the current recommended work factor for bcrypt is 7, and that seems to be a good value for the hardware that's out there today. It seems people think it's going to be really, really impossible for anyone to break a bcrypt hash with a work factor of 7. But in 10 years, CPUs might be twice as fast, and in that case, you can take your hashes and bump up the work factor to 8, and then it's going to the difficulty is going to scale with modern hardware. So they're designed to be slow, and they're designed to get slower to keep up, or not to iterate more, to be more computation, to keep up with hardware. So there are implementations of bcrypt in Ruby, Python, Node, and any modern framework you're using. There's probably an implementation of bcrypt that you can drop into it.
When you say slow, like,
they're not so slow that that your user, when they're logging in, are going to be sitting there waiting. I would say on the order of a second for a bcrypt hash, but again, you can adjust it. So if you aren't running a super security sensitive operation, you can take the work factor down, get faster hashes. Though of course, I think anyone handling passwords is an extremely security sensitive operation because users tend to reuse their passwords on all their sites. So. Okay, so going on to the next step here, another thing that I kind of glossed over a little bit is session cookie generation. So how do we come up with this session cookie? the most important thing about it is that you probably shouldn't generate it yourself. You should use a framework that generates it for you and has a user account system and a session framework in place already. And what those frameworks are going to be doing is generating a random unguessable string for the session cookie. So the most important thing about it is that an attacker can't guess it, because if they could guess it, they could impersonate the user. Another couple of things you might want to know about are these two cookie flags. So these are flags that the server sets on the cookie when it gets sent to the client, and then the client has some kind of extra secure protection around that cookie. So, excuse me. The HTTP only flag is a flag that says make this cookie only accessible by sending it across the network over HTTP, not accessible to JavaScript. So normal cookies, you can read them in JavaScript by just running document.cookie. HTTP only cookies, you can't read, they won't show up in document.cookie. And this is kind of a defense in depth mechanism. It's recommended that you use it because if you have some other vulnerability on your site, like a cross-site scripting attack, which I'll talk about in a little bit, that can allow an attacker to run arbitrary code in the user's browser on your site. And if the cookie were accessible to JavaScript, then that arbitrary code could read that cookie. So this is a protection against JavaScript reading session cookies. This is a protection against if you have some configuration mishap in your site and you accidentally have a session cookie going over a non-SSL connection. What this secure flag will do is it'll tell the browser only send this cookie on SSL connections, don't send it over just plain HTTP. So this is a good defense in depth mechanism. If you forget to scope your cookie correctly, or you accidentally have some place on your website where you're accidentally sending cookies over a non-SSL connection. So I highly recommend you check out, make sure that in your sites these flags are being set on your session cookies. And in most frameworks, I think you can just either they're enabled by default or you can just change a flag in your settings to get them enabled.
How to do it in Meteor?
We don't have cookies. I'll get to that in a minute. I swear I didn't plant that question. So. Actually, speaking of Meteor, this is kind of what a Meteor auth flow looks like, and you'll notice it's quite different from a traditional auth flow. So I mentioned this DDP connection that gets set up over WebSockets, and like I said, this is a stateful connection. So how a Meteor client logs in is it sends some credential to the server verifies it, sends back a random token, which is sort of like a session cookie, except that it gets stored in local storage, which is kind of browser storage that sticks around for some amount of time, but doesn't get sent on every request like a cookie. So after the client has logged in, this connection gets marked as authenticated, and any messages from the client after this, they act on behalf of the user. They're authenticated messages. Now, if the client closes this connection and later goes to open a new connection, it can use this token in local storage to log in with the server and authenticate that second connection. So the reason that we don't need to use cookies is because we don't have to re-authenticate on every request. We have a token and we use it once to authenticate this connection. So I talked about logging in with the oh, sorry, was there a question?
Yeah.
Oh,
the local storage, is that like the HTML5 local storage?
Yes. So I said you could log in, send a token as this credential here. I'm missing some slides. No, sorry. Okay. So we store the token in local storage. What this means for us is that we are immune to another kind of attack called a CSRF attack. And a CSRF attack, I'm just going to talk about briefly. Most of your frameworks probably have automatic support for this built in, prevention of CSRF attacks built in. In a nutshell, a CSRF attack is kind of when one website issues a request to another website from your browser, and that request is authenticated, so it acts as you. An example is we have this bank here, and you go log in at this bank. It sets the session cookie in your browser. Then you go get tricked into visiting evil.com. And evil.com sends a request from your browser to this victimbank.com website, and that request gets sent with your session cookie. So this request acts on your behalf, and this is your $100 million. So what, and you know, how can you, evil.com can send a request by a variety of ways. It can maybe put a hidden form in the page, and that form's action attribute points to victim bank, and then it has JavaScript, which automatically submits that form. And so this site is sending an HTTP post request from your browser to this server, and that request is acting on your behalf. So normal frameworks kind of prevent this by requiring a secret token that only this site knows that has to be submitted with every request. But this is very much a cookie problem. This problem comes up because there's this cookie floating around in your browser, and that cookie gets sent on every single request to your browser, or from your browser, regardless of whether who originated that request or why. There's just no choice in the matter. So in Meteor, we don't have this problem because we don't have cookies, and because we have our tokens stored in local storage, and those tokens are only used to authenticate connections when code deliberately reads them out of local storage and uses them to log in at the server. And there's a little bit of a cost here, which is that we can't use these flags that I just talked about. So the local storage token kind of has to be accessible to JavaScript, because that's how Meteor apps authenticate to the servers. They have JavaScript code that reads the token and sends it to the server. So we can't have these defense in depth cookie mechanisms, but in exchange we get kind of complete immunity from CSRF attacks. And as I said, local storage is segregated by origin, like many other things in the browser. So only your app can read out that token and authenticate as you. Any questions about this? Okay, so now I'm going to take a slight diversion into math. And what I'm going to talk about is how clients in Meteor authenticate with a password. So I talked about you log in with some credential, and then you get this token back, and you can use that token to authenticate on other connections. I'm going to give a very high-level overview of a protocol called SRP, Secure Remote Password Protocol. And this is a protocol you don't see deployed on the web very often, but it's a cryptographic protocol which has a lot of great security properties. And the most fascinating thing about it is that a client uses a password to authenticate to a server, and yet the server never sees the password. And the server never sees anything that can be useful for authenticating as the client. And if you are listening on the middle of the connection, similarly, you don't learn anything that's of use to you if you want to steal the password or act on, or trick a server into thinking that you are that client. So this is a very high-level overview of it, but I'm going to try to give some kind of intuitive feelings for what the security properties it provides are and how it achieves those. So we have a client and a server. The client has a password. The server has these two values from that it got from the client when it registered. So one of these values is assault. You can think of that just as kind of a random value that was chosen when the client registered. The other value, this one, is called a verifier. And this is kind of a mathematical function of the password and the assault. The important thing about it is that, cryptographically speaking, seeing this value gives you no information about the password. So it's computed from the password, you can't compute it with the password, but just seeing this gives you no information. And this is kind of a parameter, it's a group element, if you're familiar with discrete math, but this is a parameter of the system, this is a hash function, and this is the salt in the password. And this is what the server kind of stores in its database. So now the client has its password. It goes to log in, and what it sends is the username that it's logging in as and this random challenge value. The server in response says, okay, the salt associated with this username is this, and here is my random challenge value. So both the client and the server pick random challenge values and send them to each other. So now the client has the password, the random values, the salt. The server has the salt, the verifier, and the random values. They're each going to take their inputs and put them through functions. And what they come out with is shared keys. So that means they put their inputs through slightly different functions, and they come out with the same key if everyone's behaving honestly. Now they're going to do, the purpose of these two messages is to prove to each other that they have the same key. So the client sends a hash of its shared key, which it computed, and the two random challenge values. The server says, okay, is this message what I expected? So it knows what it expects because it knows the random values and it knows its shared key. So it makes sure that this message is what it expected, and then it sends back this message. And to compute this message, it takes this whole hash, concatenates it with its shared key, and hashes that whole thing. And the client can say, okay, I have my shared key. I know what I think the shared key is. And I have this message that I just got. I'm going to make sure that this hash is what I expected, what I should get if the server has the same shared key as me. So now they've both proved to each other that they have computed the same shared key. And the property of that shared key is that the client can't compute it without the password, and the server can't compute it without the verifier. So they've authenticated each other. The sort of intuitive feel for the security properties that you can get out is something like this. So imagine you're a man in the middle. You're trying to learn something useful just from sitting on the network and eavesdropping on these messages. You see some random values, you see a salt, you see other random values. The salt's really just a random value, it doesn't help you much. And then you see some one-way hash functions from which you can't learn anything. So the man in the middle doesn't learn anything except that he just learns the messages that he just saw. Those don't tell him anything about the password. It turns out the man in the middle also can't use these messages to authenticate later to the same server as this client. So the reason for that is because of these random challenge values. And you can kind of see that if you left out one of, if you said, okay, imagine this protocol didn't contain this server random value. If I were a man in the middle then, I could listen on an exchange. I'd see a username, random challenge, salt, hash of a shared key. Oh, come on. Worst possible sentence to go to sleep in. Okay. So I would see the username, random value, salt. Imagine this didn't exist. The hash of the shared key and the first random value, but not that one. What I could do then is then go replay these messages to a server. So I would say, here's my random value. The server would send me back the salt. Now I have a valid hash, so I send that back because there's no R2. And then that's fine. So I've authenticated as the client. If you add in this random value, then when I try to replay the messages, the second time the server would send back a second random value, and I would no longer have a valid hash of that random value. If I don't have the password, I can't compute the shared key, and I can't compute the hash with the server's challenge in it. So that's a very high-level kind of intuitive feel for its security properties. I'm happy to point you to some references afterwards if you're interested. The high bits are that this is a protocol where you can authenticate to a server without the server ever seeing your password and without anyone eavesdropping on the network ever being able to authenticate as you. And this is very different from if someone broke your SSL connection to a traditional website authentication, they just have your password. So you might ask, why aren't all web apps using this? Maybe it's a good trivia question. Why do I say here client-side crypto is almost useless? If I were a server participating in SRP, what could I do in a web app to learn the client's password even though this protocol that I just showed doesn't tell me anything about the password?
Hack the browser.
Hack the browser.
Find a vulnerability in the browser itself.
It's actually much easier than that.
Okay.
Back there.
Send malicious code along?
Yeah, exactly. In a web app, the server is providing the code that runs SRP. And this is why I say client-side crypto is almost always useless, because when the client's doing crypto to protect itself from the server is the one providing the code. So all the server needs to do is send some code that reads the password out of the password field as the user's typing it. So why is Meteor using it then? We have this protocol called DDP, and we are anticipating and already have non-browser clients. So you can have a mobile app that talks to a Meteor server over DDP, and we want to have the best possible security properties for those clients, even though we don't get a whole lot of security advantage out of using SRP on the web. Okay, so I'm finally done with my monster authentication section. The takeaways are, for this very security-sensitive code, it's important to use a framework implementation that's been well-tested, well-studied, and probably, hopefully, not super buggy. Hopefully you can drop into your framework's implementation some security enhancements, like using bcrypt, and using these secure cookie flags, which provide defense in depth. And I think it's interesting to think about the future where we might have more long-lived connections, more stateful connections, and one of the interesting security properties that comes out of this is that we actually don't need cookies at all. So now I'm going to go into cross-site scripting attacks. And this is something a little bit different. I think of it in a different category because Meteor apps are still very much vulnerable to cross-site scripting attacks. We do what we can to prevent them, and we have some plans, which I'll talk about, for preventing them even more. But this is something that I think all web developers need to worry about today, no matter what your framework, what tools you're using. So I'll start with a description of a cross-site scripting attack. I apologize to those who have seen this section of my talk before, and you're not allowed to answer the questions. Okay, so what's a cross-site scripting attack? In a nutshell, this is what happens when an attacker provides code to an application when it expects data, and the application ends up executing that data as code. So here I have a bad guy, and the bad guy is posting a comment on this website. And you can see the comment that the bad guy posts looks an awful lot like JavaScript. And now we have a victim called Alice who goes to view the comments page on his website, and what she gets back from the server is this HTML, and how is her browser supposed to know that this, which is the attacker's comment, is not a legitimate script tag with JavaScript that the browser should execute? And what happens, in fact, in this case, is that the browser does execute this as JavaScript and ends up sending the attacker the value of Alice's local storage. So this is your basic cross-site scripting attack. And what a lot of frameworks, including Meteor, do is try to kind of prevent these basic attacks. And how it does that is by taking these special characters, and it automatically HTML encodes them when these characters are rendered inside template variables. So you can see this would kind of foil that basic cross-site scripting attack that I showed, because the browser would see these as HTML encoded, and it would treat this whole thing as a string instead of parsing a script tag and executing the JavaScript inside it. So this is good for foiling the basic attacks. It doesn't foil all of them. So here's an example where we have a user profile, and the user gets to provide their username and the URL to their website. So if you can imagine Alice visiting an attacker's user profile, can anyone think of a value that the attacker could provide for their website that would result in some malicious JavaScript being executed in the user's browser? Given that those HTML characters I showed are HTML encoded. Any guesses? So the answer is called a JavaScript URL. And this is a special protocol called JavaScript, and how the browser interprets this protocol is when you click on this link, it executes the JavaScript inside the link. So the attacker is going to provide this value for their website, and when Alice, visiting the attacker's profile, clicks on this link, they are going to have this JavaScript executed in their browser. And in this case, it just pops up the value of local storage, which doesn't seem particularly harmful. And if you were trying to actually write an exploit here, one thing you might run into is any kind of interesting JavaScript you can imagine putting in this URL. it's probably going to need some quotes to do something interesting, or some single quotes, double quotes, angle brackets, all those nice characters that are actually HTML encoded. And if you put them in there, then when the user clicks the link, that would cause a syntax error. So any interesting thing you might want to do, you're going to need some quotes. What can you do that's interesting without quotes? Turns out JavaScript has this awesome feature which lets you turn strings into code and which lets you construct strings. So these are the ASCII character codes for some malicious JavaScript. You pass them into this function which produces a string, and then you eval it. So the lesson here is that having untrusted user input inside URLs in your templates is extremely dangerous because it allows the attacker to just execute any arbitrary JavaScript that he wants in the user's browser as soon as they click on that link. And there are other culprits. So you might imagine there's not much bad stuff that can happen from putting untrusted user input inside CSS. So here maybe we have a user profile page where the user can set the background color on the page. So it turns out that some older versions of Internet Explorer actually have a CSS extension called expression. And it meant well, but the upshot of it is that you can execute arbitrary JavaScript inside CSS. So if you put untrusted user input inside CSS in your templates, you are opening up your IE users to arbitrary JavaScript execution. And to be fair, it's not just IE. Firefox had in some versions something called Moz binding, which was a very similar attack vector. So the moral of the story is that it's very, very dangerous to put untrusted user input inside URLs, CSS, HTML attributes in general. You generally, in preventing this, want to go the route of whitelisting whitelisting rather than blacklisting. So you might imagine taking your URLs and making sure that they don't start with JavaScript. Turns out many browsers will still parse this JavaScript protocol if you put white space in the middle of the word. So blacklisting opens you up to the attacker creatively trying to get around your filters, and it's much better to go with strict checking or whitelisting. So for example, making sure that URLs start with HTTP, making sure that if you're going to put untrusted user input inside CSS, it comes from a list of safe values. And there's a newer mechanism called content security policy, and this is only supported by newer browsers, so you want to do your whitelisting and strict checking in addition to this. Content security policy is a mechanism where you send an HTTP header from the server to the browser, and that HTTP header tells the browser where content on your page is allowed to be loaded from. So, for example, you can specify content security policy that says, all content has to come from my own origin. Or you can say, scripts are allowed to use eval, but not be inline. So you can't have inline scripts, or the other way around. You can specify all sorts of things about where content on your site can be loaded from, and it's a great defense in depth mechanism for protecting users on newer browsers. One final thing, I said that Meteor doesn't do everything to protect you against XSS. We try by automatically HTML encoding those special characters, but that doesn't prevent all attacks. Something we want to do in the future, that because we can kind of control the full stack in this framework, we render the templates on the client, and because everything is reactive, we end up doing a lot of the template rendering as the app is used. So what I mean by that is, in your template, you have a value, and as that value changes, we take care of re-rendering that template. So it's not like in traditional web apps where, as the value changes, there's JavaScript code that goes and puts new values directly in the DOM. So we kind of control throughout the lifetime of the app where data flows into the template. And because of that, we are in a position to be able to do what's called contextual standardization. And that means maybe in a future Meteor, you might be able to say something like, Meteor, don't allow JavaScript URLs anywhere in my application. And we would be able to enforce that because we control the rendering throughout. So that's about all I wanted to cover today. I think the big takeaways are use SSL everywhere, use framework implementations when you can, keep up on the new mechanisms like the HTTP only flags, content security policy, new things constantly being developed that are great for protecting users on those browsers. I talked a lot about how the security territory kind of changes with Meteor, and my intention in doing that was not, as much as I love Meteor, it wasn't to say you should go use Meteor, but to kind of give you a feeling for how web security is a very rapidly changing area, and some of the things that 2 years ago were just axioms are now kind of changing, new attacks, old attacks becoming obsolete, and I really hope that you found that interesting. So thanks for having me. Any questions? Yes?
So if you're requiring a sticky bit to a server, doesn't that make deploying new code harder or impossible without messing up the client's currently in that state?
You mean in Meteor?
Yeah.
So we have a mechanism called hot code push, where when you change files in your Meteor app, those changes automatically get sent to the client, and so in some cases the client sees a refresh. Some of the state is preserved across page load, or there are mechanisms in place to make sure that the page doesn't refresh as the user's typing or something like that, or have the template re-render as the user's typing. I don't know a whole lot about that part of the system, but the general idea is that we actually watch files in your application, and as they change, we push that new code to the client. Does that answer your question?
Kind of.
Not at all.
It's an answer, but I would think that's asking for side effects if you're doing a pretty invasive, upgrade to your code and your deployment. Whereas if you're stateless, if you're rolling deploy, you can upgrade things. Like I said, pretty invasive.
Well, I mean, the fact is a lot of apps are already doing either WebSockets or HTTP polling, and they're kind of simulating long-lived connections, in the anyway. So I don't think we're the only ones doing this. But like I said, I don't know a whole lot about it.
Just cookies though, you can bounce people from different servers.
I mean, you can reconnect when a client gets disconnected on a DDP connection, they automatically try to reconnect, and on the reconnect they read the token out of local storage and log it
Can
in.
you go to a different server then?
You can.
Yes.
Oh, okay.
Yeah.
Then you're okay.
Yeah.
Okay. Good
All
to
right.
know.
Maybe I misunderstood
Yeah.
the question. Okay. Great. Any other questions? All right, thank you. Feel free to email me or